Until today, the algorithms we have been looking at for logic have been symbolic, at least in principle. For operations like resolution, unification, DPLL, clever data structures do play a crucial role in obtaining performance, but in principle they are symbolic, and the way they process formulas and produce proofs can be written out purely in terms of formulas on the page. Today we are looking at something quite different, something that can only be regarded as a data structure, a very efficient data structure for dealing with propositional formulas. These binary decision diagrams, or BDDs. A BDD is a canonical form for propositional logic. In general, a canonical form is a unique form. If you have a canonical form, that means that when you transform whatever you begin with into the canonical form, all equivalent formulas, or whatever it is that you're canonicalizing, will be translated to identical canonical forms so that you can test equivalence simply by testing whether the canonical forms are identical. Now, in this case, the BDD is a canonical form only for a particular order of the propositional symbols in the problem. Moreover, we insist that in this data structure, it is a tree-like data structure, while really it is a graph. We require identical subtrees to be eliminated by sharing, and we use other tricks to obtain better performance. Strictly speaking, and if you're looking in the literature, you might see these described as OBDDs or even ROBDDs. So the full, and it is a mouthful, the full name is reduced ordered binary decision diagrams. The ordered referring to the ordering on the propositional symbols, and reduced as referring to the elimination of all redundancies from the diagram. So it is only these reduced ordered BDDs that are the interesting ones that we're going to be talking about in today's lecture, that give us a canonical form and that give us a highly efficient means of working with propositional formulas. It turns out a BDD gives you a compact, exact representation of the truth table of the original formula. So in particular, you can instantly see if a formula is a tautology because its BDD will reduce to 1. You can detect if it's unsatisfiable because its BDD will reduce to 0. And in the general case, you will have some sort of non-trivial BDD, and it will have paths to 0 as well as paths to 1, from which you can read off the models and the counterexamples. BDDs emerged around the late 80s and were soon found to be very useful for verifying certain digital circuits such as adders, and have since found many other applications. Now, how do we actually do them? Well, that is actually a tricky business, and first I want to consider the question of what are BDDs in principle. So let's look at this very simple propositional formula here, and if you just consider the truth tables, we get a binary tree looking like this. So this is a fully unreduced binary decision diagram, whereas you can see the dotted line means if P is false, the solid line means in this case if P is true, and likewise here this dotted line means Q is false, and so on. So you can evaluate this formula for different combinations of the variables simply by following your way through this binary tree. I've highlighted this 0 here because it is a little different from the others. So if you wonder how we get to this 0, if P is false and Q is false, but R is true, the formula evaluates to 0. And you can check in the original formula that this is indeed the case. And so on for the other 8, well, for the other 7, I should say, paths through the formula, that is from the root of this tree down to the bottom. If we think of this as a data structure, we'll note that there's a bit of waste here because these 3 subtrees with R going to 0 and to 1 are identical, and it seems like it is a waste of space. It turns out it is, and the first thing we need to do is get rid of them. If we get rid of the repeated subtrees, we have this thing on the left side of the slide here, where in particular there, the 3 copies of R going to 0 and to 1 have been reduced by a single one, and all of the paths that were going to different copies of it now all are directed to this one copy. On the other side, you may recall that the leftmost occurrence of R had 0 underneath both the false case and the true case, so we've drawn it like this. Looking at this diagram, you might wonder, why do we bother with this test on R when it doesn't change the outcome? Regardless of whether R, in this case, is true or false, the result is 0. We should get rid of this test. Likewise, over here, whether Q is false or true, the result of the evaluation will be determined by something that comes after it. So this test on Q is redundant. We get rid of that, and we end up with what you have here on the right side of the slide. This is a BDD. So you will say, it's trivial, right? All we have to do is make the full binary tree and then collapse it down, and we've got a BDD. The problem is, if you want to do this for 100 variables, which was already possible in 1986, you would need to start with a binary tree that had 2 to the 100 nodes in it, which is a lot of nodes. They certainly didn't have that much memory in 1986, and they still don't. So the trick is to somehow convert directly from a formula into a BDD like this without going through the exponential process of making the full binary tree to begin with. Another point to stress is that unlike almost all the other proof methods we've seen in this course, we do not get rid of symbols such as implies, if and only if, or exclusive or. We haven't actually used exclusive or. It's not often seen in logic, merely for traditional reasons, but it is certainly used a lot in hardware. With BDDs, we can deal with them directly, and we do not expand them into other symbols. And this obviously gives BDDs a great advantage if the thing you are working with has many occurrences of these symbols, as in the case of an adder circuit in hardware. So our technique for converting a formula to a BDD, just from a general point of view, we'll see the details later, it will be recursive. So we start with a formula, we will recursively convert its immediate subformulas to BDDs. And once our recursion has terminated, that is to say we have now BDDs for the operands of our logical connective, then we need to cleverly combine those BDDs with reasonable efficiency and respecting all of our ordering and sharing conditions. It may be necessary at this point to delete some redundant variable tests, so we do that. And just as a remark, these days some BDD packages can routinely cope with 100 million nodes in a BDD, so we are interested in handling big problems. Now, to start off easily, let's consider the case of negation. That is to say, we started with a formula of the form not A. We recursively convert A to a BDD. And of course, we can do that conversion simply by, shall we say, let's assume that recursion works and we have got a BDD for the body of the negation. How do we implement the negation itself? It turns out to be very, very simple. We look at the topmost variable. And by the way, this if is, well, I'm trying to represent symbolically something which is really graphical, and we will see a more realistic treatment later, but just something that I can show you in printed form. I was starting with this. So if we have a variable test on P where true is linked to the BDD labeled X, so this X refers to a BDD, not to a variable, and if when P is false, we link to another BDD Y, what do we do? Well, a naive student might say simply exchange X and Y, but that is wrong. If you do that, what you're actually doing is negating simply P in the formula. You're not negating the formula itself. The correct way to treat it is to recursively apply the negation algorithm to X and to Y. Now, why is this right? Well, the negation of a BDD represented by Z, remember that every BDD is representing an entire decision tree. So now if we want to represent the negation of the original decision tree, what we say is, for any decision on some variable P, we take the true case, and when P is true, it should return the negation of what the original BDD was going to give us. Equally, if P is false, we should get the negation, once again, of what the original BDD would have given us. So if P is false, the original BDD would have got the result from Y. Now we must get the result from not Y. In fact, the action happens in the base case. So if our BDD is simply 1, the negation of it is obviously 0. If the original BDD is 0, then its negation is obviously 1. And there's a very important point here. As you might see, the action is actually happening in the base case where the truth table kicks in and does the correct thing. So you see the effect of all this is simply to make a structural copy of the BDD identical except at the very bottom where we have 0 and 1 exchanged compared with the original BDD. And it now should be obvious that in this new BDD, you will always get the negation of what the original BDD would have given you. Now, in a moment, we're going to look at the canonical form algorithm for binary connectives, but I will just like to mention that for certain binary connectives, if you apply the canonical form algorithm, they will in fact behave essentially like this negation algorithm here. And that is because Z implies 0 and Z if and only if 0 are logically equivalent to the negation of Z anyway. So, what about binary connectives? And I should say, if you can't follow this, look at the examples later, because I accept this is totally impenetrable. But let's continue. So let's suppose we are trying to convert a conjunction to a BDD. By recursion, we have already converted both operands of the conjunction to BDDs. So namely Z and Z prime are BDDs, and we want to create a BDD representing their conjunction. First, please note we know the answer already if either operand is 1, because if one of the operands is 1, then the BDD for conjunction will be the other one, right? And if either operand is 0, then the result will simply be 0. That is, anything ANDed with 0 is 0. So once again, the action is happening in the base case, because what I've shown you here, where I have all these ANDs everywhere, I have AND in here because the thing we're doing in the first place is AND. But if instead we were doing OR, all of those things would be OR. If we were doing if and only if up here, if this were the BDD for if and only if, so let me remind you again, we can do the BDD for if and only if and exclusive OR without converting them into some other connectors. We would do the exact same thing if and only if here, if and only if in all these recursive calls, and the only difference is how we handle the base case. So if we want if and only if as our connective, then we would need to treat the 0 and 1 cases as should be done for if and only if, rather than, in this case, for AND. So I want to stress the easy case because I know this is not so nice. So to remind you, when I write if pxy, it's because I don't know how to draw diagrams so well. And so this, I really mean a BDD with p at the top, x branching from the true link for p, and y from the false link for p. And similarly, we have another BDD for the other operand with some variable p prime at the top, which leads to x prime and y prime. Now, I'd like to say that it is much, much easier to understand if both of the leading variables are the same. Because then we are deciding, we're making a decision on p, if you like, or we are considering the two separate cases for p, namely p is true or p is false. What will our final BDD do if p is true? Well, it must get some value from the part of the BDD which p links to here, which is x. It will get a truth value from over here, the BDD for x prime, and then they'll be ANDed together. And that is why the BDD, again in the case where both top variables are both equal to p, the result will be a test on p where the true part, the true case for p, will link to a BDD obtained by recursively ANDing x and x prime. And in the false case, recursively ANDing y and y prime. Now, what about the other two cases? Well, they're symmetric, so I'll just look at one. You see, if the top variables are different, P comes before P prime, and since we must test the variables in order, we need to test P. We cannot test P prime because then it would be out of order when we came to P. So we do a test on P, and if P is true, we go to X, which is what P leads to. But why, oh dear. And that is a mistake. No, it's not a mistake, sorry, I'm just not awake. If P is true, this part leads to X, and the other part is the whole other BDD, Z prime. Likewise, if P is false, the result is obtained from Y, because that's what we get if P is false, and the whole other BDD. The point is that this BDD Z prime is not doing a test on P at all. Now, for doing BDDs by hand, this kind of reasoning is not very easy for us, and what you should do instead, although it is very sneaky, is you can put a redundant test on your other BDD, so putting P at the top with links true and false, both going down to Z prime, and that way you have cheated by making both BDDs start with P at the top, and then you only ever need to remember this top rule here, and then you can forget the others. Now I have a really teeny tiny example here of confining the BDD of P or Q. So in blue we have the original BDDs, and then adding in red we have the final one. The BDD of simply P, I hope it's obvious. If P is false, 0. If P is true, 1. This BDD represents the formula P. And similarly, the same idea for Q. What about P or Q? Well, in this case, it's almost too simple to try and work it out. Clearly, but we can consider cases on P. If P is false, it goes to 0. Now 0 ORed with anything is the other thing. We are ORing it with this BDD over here. So when P is false, we need to link it to the other operand. If P is true, the result is 1. And over there you see if P is true, the result is 1. Now you see that I have drawn the result on top of the original operand. That is not merely to save space on my slide, but to show you how it will actually work in computer memory, because there must never be more than one copy of anything. So this Q BDD here, it not only can be reused, but it must be reused because we insist on maximal sharing. This is not merely an optimization to save space, but part of the very idea of a BDD. Now a slightly more complicated example, and I hope you recognize our little formula that we saw already in the second lecture. So let's assume that we have converted P or Q and Q or R to BDDs already, and we merely have to combine the two. And by the way, you might want to check that this is, on the left here, is the correct BDD for P or Q. How do we know that? Well, P or Q is false. The only way it can be false is when P and Q are both false. In every other case, it must be true, according to the truth tables, and this BDD has the same behavior, therefore it's correct. Q or R is correct for the same reason. How do we combine them? And once again, if you're doing it on paper, you might find it a lot easier if you cheat and write, maybe using a very faint pencil, a redundant test with P at the top above your other operand so that they both start with P. That will probably make it easier for you. And now you simply have to do the two cases. So P is either true or false. Let's look at the easier case. If P is true, remember true implies anything is the other thing. And I'm sorry, I should have taken my own advice from before and done this in red above, so I don't quite know why I didn't hear. So this QR business actually shares memory with this one. In other words, they are the same entity in memory. If P is true, it goes to that. What happens if P is false? P is false, then we do a test on Q. Now, if I were demonstrating this in the lecture hall, I would have my two fingers out now, one over this Q and the other over that Q, because we are comparing the two formulas and working out what happens. When Q is false, this side goes to 0. 0 implies anything is true. And what happens when Q is true? When Q goes to true here, the result is 1. When Q goes to true here, the result is also 1. 1 implies 1 is true. So you see, regardless of whether Q is false or true, the result will be true. And that is why in either case, when P is false, the result is 1. Now for something much harder. An exam question from long ago. It asks for the following BDD. Now the wording of the question suggests that we are allowed to cheat a little bit by writing down directly the BDDs for the two operands of this conjunction. So let's see if we can simply write them down using a bit of brain power. First, we know it says alphabetic ordering, so P has to be tested first. And we know that if P is false, because it's an implication, the result is false. If P is true, on the other hand, the only way to get a true result is if both Q and S are true. So we draw this little thing, we say Q is true and S is true, the result is true. All other paths lead to false. And once again, we see how these BDDs very simply encapsulate the entire truth table of the formula. What about this one? Well, this has been cleverly written to fool any students who have forgotten about the ordering, because if they test S before R, then they've already got everything wrong, and there is no recovery from getting the order wrong anywhere. So you need to know that you must test R first. If R is false, this will come out true by the truth tables for implies, so the whole thing will be true. So if R is false, it goes to true. If R is true, then the whole thing collapses to S. So those are the two operands written out. Now the question as a whole is a good test of the two-finger algorithm. So let's flick ahead and see the answer, which is this. And let's see if we can get some idea of how to get here from there. So remember, we must test our variables in order. The variable at the top here is P, and over here we need to pretend that the variable at the top is P, if you like, by drawing a couple of redundant tests as mentioned before. Now, of course, that is only for the two-finger method. Computers do not have fingers and they compute BDDs rather differently from us. So, if P is false, it evaluates to true. The first operand evaluates to true. And of course, true and anything is the other thing. So if P is true, we should have a link directly into this RS BDD. Looking ahead again, if P is false, it indeed goes right into this RS BDD. What happens if P is true? Well, it's a little more complicated. Again, we need to pretend there is a dummy Q test above here. And let's do the easy case first. If Q is false, well, then the left operand goes to false. False ANDed with anything is false. So we would expect then the P true, Q false case to go to false in the final result. P true, Q false goes to false indeed. Leaving us, and again you see why it's good to have two fingers. We have one on right here now. So on the case where S is true. And over here as well, you're trying to go into here. We will have to insert a dummy test on R. You see, sorry, we can't go into S just yet. R has to be tested. So you might, if you're doing this on paper, draw a little R in here just to remind you that there, whether R is true or false, you will eventually end up in S. But so what happens if Q is true? You will have then a dummy test on R where regardless of whether it's true or false, you will end up in S. And over here, if R is false, it goes to true. And if R is true, it goes to S. And I see I have slightly got a thing wrong here. I drew out the operands for you separately, I guess for the sake of clarity. But if you look carefully, you'll see that these two S things are the same, and in a real BDD system, they would have been shared at the very beginning. I guess one reason for me to make them separate for you is because it would be an unholy mess if they were shown as they are really laid out in memory. But you need to imagine that this S bit of the BDD here and that one there are in fact the same thing in memory. And that's how it finally turns out. I don't think I can quite keep all the details in my head without drawing them. It finally turns out that if Q is true, we end up with a link back into this thing, and this is the final result. I can't claim that I have worked out every single detail of the exam question right in front of you, but I hope this gives you a head start in doing it, and you do need to have this sharing in your final result. So if somehow you overlooked it, then you got it wrong. So a reminder of some of the things I've been telling you. So doing it by hand, and of course you only do BDDs by hand if you're doing exams and exercises. I do think it helps to draw out your BDDs, use two fingers to show you what's happening with, for example, Q in the left side and Q on the right operand of your symbol. Be sure to test your variables in order. Consider inserting redundant tests so that you're always testing the same variable with each finger. Of course, keep an eye on the sharing of common sub-expressions because every identical structure has to be copied in the final result. And finally, a lot of students, maybe they have seen one of the earlier examples, and a fair number think that the way you combine BDDs is by sticking one above the other and then trying to disentangle it somehow. When you do that, you get a BDD in which you have, for example, a test on P followed further down by another test on P. That doesn't make any sense, and that is a clear sign that you have gone totally wrong somewhere. There are some techniques which are not part of the BDD concept per se, but which are important to get reasonable performance. Among them, well, we never build the same BDD twice. I've said that. That's actually part of the concept. So we are always maximally sharing BDDs. That means in particular that if two BDDs are logically equivalent, and remember when I say a BDD here, I'm thinking of a machine address of a data structure in memory. So if those two BDDs representing formulas are logically equivalent formulas, then the actual bit patterns of those addresses are identical. It also means we can test for a redundant test trivially, because it is enough to test whether the true and the false links from a particular variable are the same. So logical equivalence is reduced to identity, which is trivial to test. Equally, if you're converting a logical formula, we know that x ANDed with x will simply be x. And so a nice simple optimization is to immediately turn that into x. These are all part of the BDD concept, I should say. They're not optimizations, but this last line here is simply an optimization. That has to do with hashing or otherwise storing frequently repeated BDD computations. So it may very often happen that the same BDD calculation, that is to say, I have a particular address X, a particular address Y, and the request to form their conjunction. It turns out that in a lot of BDD operations, the same calculations are done over and over again. So it is possible to keep a hash table in which you remember these previous calculations. Now it's true that even if you didn't do this, you would still end up doing the maximal sharing because the rest of the system would guarantee it anyway. The point here is simply to avoid all the work of going through all the recursion and so on to obtain the answer that you had already obtained previously. Now, in BDDs and in SAT solvers, we have powerful and fully automatic approaches to solving propositional logic formulas. So which one should we choose? Well, first I need to say that both of them are potentially going to take exponential time because Boolean satisfiability is still NP complete. They do often give us excellent performance, and they tend to give us excellent performance on different types of problems, although both types of problems need to exhibit some sort of regularity that is not present in the worst case exponential examples. The little timeline at the top is sort of interesting. The original experiments by Davis, Putnam, and their colleagues could handle up to 10 variables. Now, 10 variables seems trivial by modern standards because we can test 10 to the 24 combinations purely by brute force today, and indeed, what did I say? 1024 is what I meant to say. And indeed we could do 20 variables, that is approximately 1 million combinations on a modern computer. But for 1962, maybe it was a breakthrough. With BDDs in 1986, it was possible to treat problems with something like 100 propositional variables. And this is clearly beyond the scope of even today. We cannot deal with 2 to the 100 in any brute force way. Then when SAT solvers were tuned in various clever ways, a process that started in the 90s, and by 2001, people could deal with problems in up to about 10,000 variables. I think today they can deal with much, much bigger problems. Incidentally, some people, typically from the hardware realm, will say that all of these advances are strictly due to advances in hardware performance. If you want to refute this, you merely need to mention that these are all potentially exponential algorithms, and when Moore's law says you double computer power every 2 years, if the complexity of your problem is 2 to the n, then doubling computer power only lets you go from n to n plus 1, which is pretty damn insignificant even over 40 years of Moore's law. So the improvements in power that we have seen for theorem-proving technologies, okay, of course it owes something to hardware, but it owes much more to more intelligent and more sophisticated algorithms. Anyway, there are some major differences between BDDs and SAT solvers. Firstly, I hope you've noticed the BDD is giving us a full summary of the formula in question. So for example, if you could remember the P or Q implies P or R formula that we've been looking at so much, the BDD immediately shows us the full truth table. It shows us the one link to false, all the other ones going to true. With a SAT solver, you get one counterexample at a time. You can ask for more, but you get one at a time. So it's giving you less, but often one counterexample is all you need. And if I want to look at my own footnote here, there's a very powerful technique in verification known as counterexample-driven abstraction refinement. That refers to situations, or rather technologies, that involve taking a situation that is in its full form infinite, so in its full form impossible to model perfectly by a SAT formula, by a propositional formula. So instead you abstract it down very crudely to a couple of bits and try to deal with it that way. You solve your problem using this crude abstraction, and then if you've got a solution, you test to see whether that solution holds in the original case. If the solution holds, then you've solved the original problem, and if it fails, that means your abstraction was too crude, and you can use the nature of the failure to refine the abstraction in a precise way that adds more detail in the exact place where it is needed and nowhere else. This has turned out to be an extremely powerful technique that allows us to make a great achievement in program analysis, for example, introducing just as many bits as are necessary to adequately represent certain phenomena in software. So returning to my slide, one nice advantage of BDDs is they handle full logic directly, including things like exclusive OR, whereas SAT solvers prefer clause form. BDDs were originally used for hardware, and I think they still have the advantage there, whereas SAT solvers have been used for all kinds of other problems, mostly more program verification type things. BDDs have been incorporated into tools called model checkers, so they can be used as an underlying technology for certain other verification tools. As we have seen already, SAT solvers can be combined with decision procedures to solve problems involving numerics, for example. So these are different technologies that you need to know how to deploy in suitable situations. Now, in these lectures, I have used alphabetical ordering simply because it's the most intuitive. But in fact, choosing the right variable ordering is a crucial step in having success with BDDs. So the formula here on the slide, it's a very simple formula. We have two n variables, and you see it is true if P1 and Q1 are true, or if P2 and Q2, etc., up to Pn and Qn. Now, it turns out the best ordering for a BDD is one in which related variables are close together. So the best ordering here is, as shown, P1, then Q1, then P2, then Q2, etc., finally Pn, and then finally Qn. It turns out there is a linear, or the BDD for our formula with that ordering has exactly 2n nodes, which means it is of linear size, has a linear number of nodes, and I can describe the BDD for you. You should be able to draw it without any fancy calculations, because clearly you test P1. If P1 is true, you test Q1, and if that is also true, then you link straight down to 1. If either one is false, you continue to a test on P2 and Q2. If both of them are true, you go down to 1. If either one of them is false, you continue to P3. In other words, each of our variables, P1, Q1, etc., needs to be tested only once, and we can determine the truth value of this formula in every case. What happens, on the other hand, if we order them like this, where we have all the P's followed by all the Q's? It turns out that in this case, the BDD we get is exponential. It has exactly 2 to the n plus 1 nodes. And the reason is, instead of being able to test P1 and Q1 and immediately know the answer, we have to test P1 up to Pn. And only then can we start to do things with the Q's, because we don't know anything about the final result until we have started testing Q's as well as P's. And it turns out, in the case of n equal to 4, we get this. I know that is not terribly legible. Nevertheless, well, there are 32 nodes there, and as you can maybe see, we have to test all the P's. There we are, testing all 2 to the 4 possibilities with the P's. And from that, we are ending up testing the Q's many times. So this is a case where the wrong variable order causes an exponential increase in the size of the final BDD. Some BDD packages can help you find the optimal variable ordering, but we must remember we're dealing with an NP-complete problem, so all we can do is hope for the best.